I'm going to start my presentation on dataset shift in binary quantification. So I did this work during my research stay in CNR in Pisa. It was 3 months last summer from June to August. And I was there under the supervision of Alejandro Moreo and Fabrizio Sebastiani. So the reason why I went there was because they are, I would say, maybe the most active research group in quantification in the world. So in my university, that is University of Oviedo in Spain, we also have a group quite active in this field. And I think it was a very good idea to go there to learn quantification with them, as we work in more or less the same field. So Mirko, 2 talks ago, explained it very well, what is quantification, but I'm going to go over it again. So really quantification is about trying to learn a model that is able to predict the distribution of labels in a test set. And we can have binary quantification or multi-class quantification, or even ordinal quantification, as Mirko said. But really, for instance, in this case, in the slide, we are trying to predict the sentiment of a set of examples and trying to predict the true prevalences. So here we have a different definition of quantification, and it's a task of belonging to the supervised machine learning field, in which we train models that we call quantifiers, their aim is to estimate the relative frequencies or prevalences of the classes of interest in a set of examples. So we have different examples of fields in which this is applied or in which quantification is used. One is in text sentiment quantification, for instance, trying to quantify in Twitter opinions or Amazon reviews, trying to quantify sentiment, so how many opinions of each type there is in a sample set. But also, for instance, in other fields, interesting examples are in biology, in which we try to estimate the prevalence of types of blood cells, and also in marine biology, in which we have water samples and we try to estimate the abundance of each of the species that are in these water samples. The important part here always is that we do not care about the individual classification of each of the plankton items or each of the tweets, but we are trying to find out the aggregate results. So as Mirko said, as well, I'm repeating a little bit here, but the method classify and count is like the obvious approach for solving quantification, and it's been shown many times that it is not an optimal quantification strategy. Here we have a basic example of 2 classifiers that we can use to make a quantification estimation, H1 and H2. And H1 actually is a better classifier than H2, but if we use it for quantifying purposes, we would see that H2 really is a classifier that is suited better for quantification. It actually will give a perfect quantification results, and this means that the approach of classifying and counting directly is not something that is good for quantification. So we say that quantification is a task in its own right, and there is a lot of literature of this field, and it's been pretty active these last years. Also, the formulation is different, okay? And in classification, we process examples, okay, feature vectors, and we try to assign labels to them. And in quantification, instead of that, we are processing sets of examples, okay? And each of these sets of feature vectors, we try to assign them a vector of prevalences, okay? And also the error measures are different. In case of classification, we have accuracy or other error measures for for classification. In case of quantification, we are interested in other errors, like, for instance, the bias, underestimation, overestimation, or measures like absolute error or relative absolute error. Another quite big difference is that in classification, we work under the IID assumption, which is that both training and test data are drawn from the same distribution, data distribution, but in quantification, this doesn't happen, okay? Because the distribution of the labels, that is the priors, shift between training and test. So we work under the assumptions of something that we call prior probability shift in the dataset shift literature. So these are a list that is maybe not extensive, but is a pretty big list of all the quantification methods that have been created in the last 20 years or 15 years. And the question why I put this is that most of these algorithms, I would say 99% of them, work on the assumptions of prior probability shift. So, and why is that? Because prior probability shift is the obvious thing for quantification, is the distribution of the labels, what changes. And here in this case, for instance, this is a chart of plankton quantification. So ciliate mix is a plankton species. And obviously, the prevalence of this species changes over time, okay? So obviously here we have prior probability shift if we take into account the training data and the testing data that could be each of the samples in which we test the system. If there were no prior probability shift, we wouldn't have a quantification problem because we just return the training prevalence and that would be it, okay? But it's not the case, obviously. So the thing about the work that I did in PISA is that in terms of dataset shift, prior probability shift has been widely studied in the quantification context. And this prior probability shift has two conditions. So the distribution between training and test obviously changes, but we say that the distribution of the priors, the class labels, change, but the class conditionals, that is the probability of X given Y, is constant between training and test set. And this is very, very important because most algorithms, quantification algorithms, work under this assumption. But the reality is that there are examples, real examples, in which these there are other types of shift, okay? Not only prior probability shift, but others. And in the dataset shift literature, there are other types of shift like covariate shift or concept shift. But the thing is, in the quantification literature, we never studied that how quantification algorithms work when they are faced with these types of shift. So this study is about this. So for instance, we have studied covariate shift. In covariate shift, what changes between training and test data is the distribution of the covariates. Okay, for instance, in this graph that you can see here, we can see that the prevalence of the classes, so the priors do not change. It's always, we have as many positives as negatives, but the distribution of the covariates change. Okay, here we have these blobs under it, they are underrepresented. And the question that is here is how quantification works under this setting, okay? So under the definition of covariate shift, we say that the distribution of the covariates changes, but what remains constant is the distribution of the posterior probabilities. And we can have also that the priors change. In this case, is the priors do not change, but we have this case here, for instance, where the number of positives has increased a lot. And we say that here the priors also change, okay? So for covariate shift, if the posteriors are constant between training and test samples, and we have a soft classifier that is able to estimate them properly, then we can say that this problem can be solved using a method called probabilistic classify and count. That is just an average of the outputs of a sub-classifier, okay? But what we have found out in our experiments is that depending on the covariate shift in particular, in real cases, okay, the estimations of these posteriors by a sub-classifier is also biased, and that means that this PCC method that in theory will work very well under covariate shift situations do not work that well. So this is something that we were studying a lot, and this is something pretty important because makes that all quantification algorithms up to date do not work under this setting. And we also have another setting that we studied is concept shift. That is another type of shift in which we have a change in the distribution because, for instance, some data points change label because any reason, okay? And this means that the class conditional, that is PDX given Y, and the posteriors change between training and test, obviously. If we change some labels, that will happen. And the reality is that we just wanted to point out that there is no quantification algorithm that is prepared to face this type of shift. It has been studied a lot in classification contexts, like also covariate shift is being studied a lot in classification, but not in quantification. Okay, so this is also an open field of research. The idea of developing methods that quantification methods that are able to help to tackle both covariate and concept shift. And some conclusions about my research. So quantification is a pretty new and unexplored task that there are quite a few researchers nowadays working on this, but there are a lot of problems still open. One of them is dataset shift. And about my stay in Pisa, for me it was great. I met many people there, in particular my supervisors, which I am friend with them now, and we are still researching together in this paper that we are trying to publish, and also in following up papers. So that's it for me. If you have any questions, I will be happy to answer them.